according to molecular kinetic theory, we had introduced an ideal gas, right? So that is this theory. So this theory is actually coming up with the equation as well. Right? This theory is coming up with the equation for gases, right? So the equation is like this: PV is equal to, another equation using the PV is equal to 1/3 m dash in c squared bar. This is the equation of molecular kinetic theory, right? So some new terms are appearing here. PV are the normal terms, the pressure of the gas and the volume of the gas. Volume of the gas means the volume of the container. So what are these new terms? M dash in and c squared bar. Yes, M dash is actually M dash is your mass. M normally represents masses, no? But remember here, it is about a special mass. It is the mass of a molecule. Mass of a molecule, one molecule. Mass of a molecule. Mass of one molecule. Remember, that is not the mass of all the gas. This is just the mass of a one molecule, right? So that is why I came up with a dash here. Normally in resource book, it is mentioned as M. Normally we come up with M for the mass of the substance, no? But when it comes to a gas, the gaseous substance, it is not good to mention it as M, because this is mass of a one molecule, right? So normally we consider the mass of the whole stuff as M, right? So per one molecule, one molecule, this thing, it could be M dash. Some different terminology should apply, right? So that is M dash, mass of one molecule, right? So N is number of gas molecules. N is number of gas molecules. Mass of one molecule into number of gas molecules in your gaseous system. Actually, the mass of a molecule into number of gas molecules will give you the total mass of the whole system, right? එක molecule එක mass එක වැඩි කරාම molecules ගානේ you get this thing actually gives you the total mass which can be denoted with the m of the gas, right? And some c squared bar is appearing, right? C squared bar is appearing. C squared bar means, that is another new terminology come in there. C squared bar is, right, mean square speed. Mean, the bar thing is used for mean, the average value. Mean square speed. Some special kind of speed, right? Mean square speed. We'll discuss what that means, right? So this is the molecular kinetic equation, right? Molecular kinetic equation. P is equal to 1/3 of m dash in c squared bar, right? Okay. So then let's discuss what is the importance of this equation, right? What is the importance of this equation? Actually, this equation explains the pressure. If you take the pressure, if you subdue the pressure, it will be like this, no? It will be written like this, no? So actually, this equation explains the pressure, right? With the use of mass of a molecule, concentration of gas, number of gas molecules in a unit volume, concentration, and kind of speed of gas, right? So actually, that is the idea. This equation explains the pressure, kind of a bulk property. Pressure is kind of a bulk property. pressure rises. We discuss the pressure for the whole system, bulk property. In terms of some molecular properties, mass of one molecule, molecular properties. Mass, this is kind of a speed, right? Average speed is for one guy, no? Average values are then, if you are to take some this kind of marks, 75, 70, and 65 marks, right? If you are to take the average, that average value is the value, right, which can be used for one species, no? Right? Again, sadharana value average value එකෙනෙක් වෙනින් යොදන්න පුළුවන් sadharana value, right? So it is for one particle. So basically that is the idea. So this equation explains the pressure, the bulk property in terms of kind of molecular properties, right? So it says when the mass is high, pressure will be high. It is very clear, no, Lama? When the mass is high, pressure will be high. The pressure is actually the force over area, no? This is pressure, no? Right? If a particle with a greater mass to collide with the walls, it will exert greater force than a particle of lighter mass. So when the mass is greater, you will insert some greater force. That means pressure would be high. So when the mass of a particle will be high, the pressure will be high. Then the concentration. When you have more particles, more gas molecules, or more particles in unit volume, when the concentration is high, then more number of collisions will happen with the walls of the vessel. So more force will be inserted to the walls of the vessel, so the pressure will be high, rather than a system with a low number of particles. Only 3-4 collisions will occur, giving you less force to the walls, right? So when the greater the number of particles or in a unit volume, or the greater the concentration of the stuff, the pressure will be high, right? So pressure has been discussed in terms of the concentration. And this one as well, when the particles start to hit with a higher speed, with some high speeds, if you are going to hit to the walls, you will insert more force to your walls, and pressure will be high. The speed also matters, right? When the particles start to collide with very slow speeds, the force will be low. If they are colliding with high speeds, force will be high. So the speeds matter. Greater the speed, the average speed, greater the pressure will be. Actually, when the force means this, no? Force means this thing, no? Rate of change of momentum, no? Right? Greater the velocities, you will come up with greater force, right? It's like this, no? Simply we can say delta mv over t, and the velocity is high. V is not going to change, lama. Elastic collisions, no? Right? When the V is high, force is high. When the average speeds are high, force inserted will be high, so that will lead to greater pressure. That is how this equation explains the effect of velocity or the speeds of molecules to the pressure, right? So with this, we are able to come up with those ideas. Let's go to the note, Lama, and see whether you clearly understood these concepts. See, molecular kinetic theory, and they have given you the equation P is equal to 1/3 of m n c squared bar, right? The terms are labeled. Then they are saying that m dash n is the mass of the gas, the simple name, mass of the gas, the simple name. That is understood, right? Then what else they are saying? This equation gives pressure a macroscopic property, the bulk property, in terms of molecular motion. In terms of molecular motion, significance of this equation is that the pressure is proportional to mass of a molecule. The pressure is proportional to mass of a molecule and the concentration of molecules and the mean square speed of molecules. Mean square speed of molecules, right? So that is the significance of this equation, right? Okay. Right. Let's discuss a bit more about this C squared bar. Let's discuss a bit more about this C squared bar thing. The C squared bar, the mean square speed, right? Let's discuss a bit more what that means. These are very clear, no? Easy to understand. No? Let's discuss about this thing, what this actually means, right? When it comes to gaseous systems, right? We define, right, some velocities, right? We define some velocities like mean velocity, right? Mean square velocity kind of things. Let's discuss one by one. Let's think of a gaseous system with four gas molecules appearing. Just to give you the simple idea, right? Let's say one molecule is coming with 2 ms minus 1, another with 3 ms minus 1, some guy with 5 ms minus 1, some other with 8 ms minus 1, right? Let's consider these velocities, the speeds one by one. The first speed discussed is the average speed, right? What is this average speed means? Average speed is actually what you know about the average, right? How to get kind of an average from a number of entities. Yes. First, just add the numbers, and then you have to divide those numbers with the number of entities you used. So means you have to add the numbers 2 plus 3 plus 5 plus 8 divided by number of entities 1, 2, 3, 4. That will give you the average value. So that will give you the average velocity, right? These are mentioned in ms minus 1, so that the value will come with ms minus 1. So that is going to be 5, 10, 18 over 4. So 4.5 ms minus 1. That is a simple idea. The average velocity is that. Just take all the numbers and get the summation of all the velocities and divide that value with the number of entities, right? Simple as that, right? Normal way of taking the average. If you think of this one, C squared bar, that is our major interest here, right? So C squared bar, what is that? C squared bar, to come up with C squared bar, what we need to do is first take the squares, then take the average. That is what this means. Mean square speed means first take the square value of these speeds and then take the mean. Like this. See, the 2 square, one particle is with 2 ms minus 1 speed, it is squared. And 3 squared. Take the square values of these speeds. 5 squared and 8 squared. Square values are taken. Then take the mean. Take the mean of that thing. Mean means you have to divide the value with number of entities you have used. 1, 2, 3, 4. This is mean square speed. What is the unit? These values comes with ms minus 1 square. 8 ms minus square, right? So that is going to be ms minus 1 square means this. Right now? M squared is 2 minus. So let's come up with the value. It will be like 4, 9, or 13, 13 plus 25, right? 13 plus 25 is 38, 38 plus 64, 38 plus 64, that is 102, no? Divided by 4. That will give you some 25.5. That is how we are supposed to come up with C squared bar. That is this, sir. Not you now see, this is not a hard stuff to understand. It is just this thing. Mean square speed means first you need to come up with the square values of the speeds, then get the mean, right? Then another term is defined as the square root of the mean square speed to get the value in the normal units of speeds ms minus 1. This value is given in some square nature, right? So take the value in normal units. You better take the square root of this thing. That means first you have to take the square root. Sorry, it's like this. First you have to take the square values, then take the average, then the square root. Right? First take the square values like this. Then take the average divided by 4. Took the average, right? Then the square root. Right? Always start with the most inert species. Squares of speeds and average and the root. So that will give you like this, no? So this guy's square root is just ms minus 1. So this number is this. That guy's square root is 5 point something. I just put it like this. Right? So you have to note that always the root mean square speed is greater than the average speed. Remember that. That is always true, right? Always the root mean square speed, this 5 point value is greater than the average speed. Right? The same units, right? Okay. So that is the knowledge you should know about the mean square speed. We'll derive an equation for this thing next week. But first, that is the idea, right? The simplest idea is of the mean square speed is just you need to come up with square values of the speeds, and then you have to take the mean. Means you have to divide it by the number of entries, right? Okay. Okay. Right. That is all about the root mean square speed. Just go to the note level. See whether you are able to understand the concepts appearing there. Definition of molecular speeds. It says when n number of molecules in a constant volume container at constant temperature travel with the different speeds of C1, C2, C3 and Cn, different kinds of molecular speeds can be written as the values are given, no? So average speed C bar is equal to C1 plus C2 plus C3 divided by number of entries n, like this, right? You can take this these values as C1, C2, C3 and C4. Right? Okay, number of entries, that means the n, capital N is equal to 4, right? Like that. So mean square speed and the root mean square speed, all the things have been defined using some symbols, right? Okay. The simplest idea is that. Right? That is very simple thing, right? You may see this as a huge one, big one when looking at the symbols, but the concept is very simple, right? Okay. Right. Badly. මේක වැදගත්ම කාරණේ ළමයි මේ section එකේ වැදගත්ම දේ තමයි when we are going to think of the questions they would ask from this section, right? The most important two things to learn is actually we need to be able to come up with some equations which derived with the use of this equation and the P equals nRT, right? So basically, with by combining this equation and the P equals nRT, we can come up with some important equations, right? Let's discuss about those two. One is for the average kinetic energy, and the other one is for the root mean square speed. I mean, for this one, right? For these things, we can come up with a good equation in terms of gas constant R for this one, as well as we can come up with a good equation for average kinetic energy, right? We'll discuss those two equations, how derivation of those two equations, right? By combining this molecular kinetic equation as well as the P equals nRT. Those two derivations should be known. ඒ derivations එක ළමයි තනියම වට කරන්න පුළුවන් වෙන්න ඕනේ. මොකද ඒවා විභාගයේ විතරම අහනවා. In term test, they definitely ask one of these derivations, right? Okay, let's go to this. First, we are going to come up with an equation for C squared bar. mean square speed. Right? Let's come up with the equation for mean square speed. Right? Mean square speed. Right? It is this. Let's try to come up with the equation for this. Right? So this is the derivation. This is how to derive, how to come up with the equation. See, we know that the molecular kinetic equation is PV is equal to PV is equal to 1/3 m dash n c squared bar. This is from molecular kinetic theory. And we all know another equation is there for the PV multiplication, which is the PV equals nRT, came from the ideal gas law. If you have to combine these two guys together, if you combine these two things, you will get 1/3 m dash n c squared bar is equal to nRT. Right now? As we all know, this m dash n is actually the mass of gas. Right? So we can simplify this equation as 1/3 mc squared bar is equal to nRT. Right? If you are to subject this c squared bar, we will come up with 3nRT. 3 comes here. This m, I am write it here. Right? Just write in the m. Right at the bottom of the n. Right? Okay. So, but we know that NOM is what? Here the NOM is actually 1 OM, no? Like this, no? The molecular weight M, which gives by the G mole minus 1, is actually the gram value divided by the number of moles. Right? So, simple MON is the capital M. So, this is the reciprocal of this thing. So, 1 OM. Right now? So, as this is like that. So, instead of this thing, we can write 1 OM. 1 OM. That will give you the C squared bar as 3. Instead of this, you can write RT. Instead of this, you can now write 1 OM. 3 RT OM. This is the equation for the C squared bar, which has been derived with the use of with the combination of combining these two guys, right? Okay. This is some equation of C squared bar, right? If you are looking for kind of the square root of C squared bar, root means square speed, that will be like this. Just take the square root of the stuff. 3 RTOM square root. Right now, this is mean square speed. This is root mean square speed. Right now? Okay. Let's discuss a bit more about this thing. අපි ගැන තව පොඩ්ඩක් දෙයක් කතා කරමු. Actually, this is the fundamental equation. This is the fundamental equation for the C squared bar. Remember that. It's a very important idea, right? So this equation says This fundamental equation for the C squared bar says that C squared bar depends only on the temperature and the kind of gas. C squared bar depends only on the temperature and the kind of gas, right? Okay, so depends only on the temperature and the kind of gas. So M is the kind of gas, right? If you are going with O2 gas rather than N2 gas, O2 gas is with a higher M than the N2 gas. So C squared bar will be low for the O2 gas, like that, right? So with the kind of gas, as the capital M varies, C squared bar varies. With the temperature you are dealing with, C squared bar will vary, right? That is the idea. C squared bar depends only on the absolute temperature and the kind of gas, right? And remember and keep it in mind that C squared bar won't affected by the pressure or the volume. Won't affected by the pressure or the volume. See, one may think as C squared bar appears on this equation, one may think that increasing the pressure will increase the C squared bar, but that is not the case. As long as you are not changing the T and M, as long as you are not changing the absolute temperature and the kind of gas, the C squared bar won't change. See, even though this kind of equation, increasing pressure with the constant temperature and constant gas won't vary the C. How come? How come? The idea is this, right? As you are not changing the temperature and the kind of gas, this is a constant, no? This is a constant. That is a constant means the PV multiplication is going to be a constant. Even though you are changing the pressure, the PV multiplication won't change. How come? The PV multiplication will be kept as a constant by decreasing the volume if you are to increase the pressure. Right? As far as you are maintaining the temperature constant with the same gas, even though you increase the pressure, PV multiplication should be kept constant by decreasing the volume. Because this side is a constant means as far as you are dealing with the same temperature, this side is a constant. So this side should be also a constant, the same constant, right? So when you are increasing pressure, what happens is the pressure will decrease to maintain this PV multiplication a constant. That is what happens here. When pressure increase, to maintain the PV multiplication constant, V will decrease and this will be maintained as a constant, right? So that C won't change. C won't change. So if they are asking question, right, with the C squared bar, always think with this fundamental equation, not with this, but go with this fundamental equation. This carries all the meaning of the C squared bar, right? The C squared bar in prashna karana making it right? So C squared bar will be affected only by the absolute temperature and the kind of gas, right? Not by the pressure or the volume. See, let's discuss some examples. See, some examples, right? Let's take the C squared bar for the N2 gas. Sorry, let's take the C squared bar for the N2 gas, right? For the N2 gas, right? With the 1 atm pressure, let's write this in. With N2 gas, with 1 atm pressure, right? and 300 Kelvin. Let's compare this thing with some N2 gas with 1 atm pressure, sorry, with let's say 5 atm pressure and with 300 Kelvin. Let's compare these two. Which value is higher? Which value is higher? This one or this one? What is the idea? Which value is higher? මේකද මේ වැලියකද වැඩි? This one is no? Both are equal. Both are equal. Why is that? We are dealing with the same gas as well as the same temperature, wherein the pressure won't affect the C squared bar. That is the total idea, right? So the values are equal, right now? That is the idea. So let's take this one. You take the C squared bar with N2 gas at 1 atm at 300 Kelvin. You are to compare that thing with some C squared bar of O2 gas right with 0.5 atm and 300 Kelvin. Tell me which value is greater than the other. Which value is greater? Which value is greater? This one. That one is greater. How come? Temperature is constant, no worries. Right? No need to look at this, right? No need. Right? Pressure is doing nothing to C squared bar. And we have to consider this matter. Right? Smaller the m, greater C squared bar. Right? So, smaller the m, the N2 carrying some 28 value, O2 carrying some 32 value. Smaller the m, greater the C squared bar. Right? That is the idea, right? So you can highlight the stuff, right, which I have underlined in red color. Let's consider another example. C squared bar with some N2 gas, right, and 10 decimeter cubes and some 300 Kelvin with C squared bar for the same N2 gas with 5 decimeter cubes and some 500 Kelvin. What is greater than the other? Which one is greater than the other? One patheke dakuණු පැත්තද වැඩි? Same gas, nothing to worry about the volume, right? Different temperatures. So greater the temperature, greater C squared bar is, right? So this one is greater. So you can highlight the temperature. Temperature, what it matters. Here the gas, what it matters. Right now, got the idea? Remember that. Pressure, no need to worry about the pressure or the volume as far as you are dealing with the same gas at the same temperature. Right? C squared bar only depends on the temperature and the kind of gas. Right? Okay, let's write the stuff, right? First, put some note like this. And let's write, put some note, and then let's write a note. Before writing the example, we will write some sentence, right? Okay. Put this thing kind of a note and write. Mean square speed. Mean square speed within brackets c squared bar, close the brackets, and root mean square speed within brackets square root of c squared bar, close the brackets, depends only on the depends only on the depend only on the red color. Again, just write it in red color. Absolute temperature, absolute temperature, and come to the normal color, and absolute temperature, and again in red color, kind of gas, within brackets capital M. Kind of gas is denoted by capital M, right? Capital M actually represents the kind of gas, right? When the gas varying, the mole mass will vary, right? That is the idea. So you can go through these examples. Let's go through these examples, and ultimately you can box the stuff. You can come up with some highlights as well. The highlights stuff are the reasons for the changes, increasements, and decreasements of the stuff, right? About the C squared bar thing, right? Okay. Let's discuss about the other equation, which can be derived by combining these two equations, right? Okay, let's go to that. The next one, right? I'm trying to derive a equation for average kinetic energy, right? You're trying to come up with a good equation for average kinetic energy, right? Actually, we have went through this equation at the beginning of the lesson. If you are to remember the fifth, if you remember the fifth suggestion about the ideal gases, there we had said that right the absolute temperature, sorry, the average kinetic energy of an ideal gas depends only on the absolute temperature. That was the fifth assumption, consideration with the ideal gases, right? So let's try to come up with that equation. There was an equation called like EK bar, the average kinetic energy, is equal to 302 kBT, right? That was the ultimate equation we had mentioned there, right? Okay, let's discuss or let's try to derive that equation by combining the two equations of molecular kinetic theory as well as the equation of Picos and ideal gas law, right? So let's try to combine. Two equations are this: Px equal to 3 m dash in c squared bar, and the Pv is equal to nRT. This is because this is the molecular kinetic theory equation This is the ideal gas law. If you are to combine these two, you'll come up with 1/3 m dash nc squared bar is equal to nRT, and this is actually the mass of the gas. The first steps are actually same as the earlier derivation. First few steps are same as the earlier derivation, so you will come up with this. Right? Then it will give you mc squared bar is as mc squared bar is equal to 3 nRT. Up to here, the same stuff have been done, right? As earlier. Okay, let's come up with some equations for the kinetic energies as well as for the average kinetic energy, right? So let's consider first for the kinetic energy. Kinetic energy of gas. Let's mention it as EK, kinetic energy, right? So we know the kinetic energy is equal to half mv squared. In this case, as the speeds are mentioned in C, right? Half mc squared, right? Now that will give you half. Instead of mc squared, we can substitute this, right? Half into 3 nRT, right? So that is actually EK is equal to 3 by 2 nRT. So you clearly see the kinetic energy will depend on two things. Kinetic energy will depend on two things. One is the number of moles of gas and the absolute temperature of gas. When the absolute temperature is high, the kinetic energy is high. When the number of moles are high, kinetic energy will be high. Right? Okay. Then the second stuff, right? After the kinetic energy, let's try to come up with some average kinetic energies. Average kinetic energy. We can denote it as EK bar, kinetic energy, the average bar. Right? So that can be derived per 1 mole of molecules as well as per molecule. Right? Okay. First, we'll come up with per 1 mole of molecules. So then what we have to do is we have to divide the kinetic energy with number of moles. Right? Number of entities per mole. Kinetic energy will be given by joules. This will be given by mole. So then you get the number per mole. Per mole, right? Okay. That is equal to the kinetic energy is written here 3 by 2 nRT. Have to divide by number of moles in. Right? So you will get the n will cancel off. Right? Then you will come up with, right? I'll write that thing here. Copy this equation, right? EK bar per mole is equal to 3 over 2 RT per mole, right? Per mole value. right? This is per mole, right? Units, right? Units are going to be joules per mole, right? So let's take for per molecule. If you have to take for molecule, you have to divide the EK kinetic energy. The number of entries is going to be number of molecules, right? We have divided by the number of entities to come up with the average value, right? So it will give you, right, the 3/2 thing is there in RT. You have to divide by it, right? Right. So let's take the number like this. It is better to take the number of molecules like this. So actually we know that N is number of molecules is equal to number of moles into the Avogadro's constant. Number of molecules means moles into Avogadro's constant will give you the number of molecules, right? So let's take the same thing as here, right? N, right? This number of molecules, right? Number of molecules, right? Okay. So these N's will cancel off, and ultimately you will come up with a kind of equation, right? That EK bar is equal to, right, 3O2. Actually, R over L is another constant, right? R means a constant, is a gas constant. L is the Avogadro's constant. So R over L is another constant. So it is referred to as the Boltzmann's constant, right? Kb is the Boltzmann constant, right? So that is the R over L value. The B is subscript, right? Subscript. So that is the average kinetic energy per molecule. Given in joules, right? That is the idea. Okay, those are two equations, and these clearly say that the average kinetic energy depends only on the absolute temperature. Only on the absolute temperature. If you take 5 moles of N2 gas at 300 Kelvin and 10 moles of N2 gas at 300 Kelvin, both situation, the average kinetic energy is same. As far as same temperature is maintained, the average kinetic energy is same. The 10 moles of N2 gas or the 50 moles of N2 gas, the average kinetic energy is same. For 10 moles of N2 gas at 300 Kelvin and for 1000 moles of O2 gas at the same 300 Kelvin, both are with the same average kinetic energy. It could be the O2 gas or the N2 gas, no worries. It could be 3 moles or 5 moles, no worries, right? If both of those are with the same temperature, as far as those are with the same temperature, 300 Kelvin, both are carrying the same average kinetic energy. So average kinetic energy won't depend on the gas because capital M term is not appearing. Average kinetic energy won't depend on the amount of moles because N is not appearing. It depends only on the temperature, absolute temperature, right now. So remember, but the kinetic energy will depend on the number of moles. Right? So complete this one, then we'll write the other things, right? First of all, just complete the derivation. This is the average values, right? මේ කතා පොඩ්ඩක් ලියා කොහොමද? Not and just write You can write in the red color pen. You can write average kinetic energy. Average kinetic energy will only depends on average kinetic energy will depend average kinetic energy will depend only on average kinetic energy will depend only on absolute temperature. Average kinetic energy will depend only on absolute temperature within brackets capital T. Right, and won't depend on kind of gas capital M within brackets capital M, or the number of moles of gas within brackets simple N, or the number of moles of gas. Right. Let's have some come up with some examples. So if you take the average kinetic energy Ke bar of N2 gas at 300 Kelvin, with let's say 5 moles of that thing with 300 Kelvin, and if you consider the kinetic energy average thing of O2 gas 10 moles, that is also at 300 Kelvin. Actually, those two guys are carrying the same average kinetic energy. As far as the absolute temperature is same, no use of considering the gas as well as number of moles. No worries, right? So we can consider another situation. You consider average kinetic energy of N2 gas with right 5 moles of stuff 300 Kelvin, and if you consider the average kinetic energy of some other gas, some say moles with some 500 Kelvin, that matters. See, the temperature changes, that matters. The greater temperature will carry some greater average kinetic energy, right? No worries about the gas or the number of moles, but what matters is the temperature, right? Okay. See, write these two examples, and that's all for today, right? Let's complete this stuff.